Değerli katılımcılar, sevgili arkadaşlar, ülkemizin bilim dostu, bilgisever, güzel insanları, herkese iyi akşamlar. Bilindiği üzere günümüzde atom ve moleküllerin yapı taşları olarak kullanılması ile üretilen nanomalzemeler, endüstriyel ve teknolojik kalkınmaya, hız kazandırmaya devam etmektedir. Aynı zamanda yenilikçi temel bilgilerin üretimi ve bu bilgilerin uygulamalı alanlara akışının sağlanması insanoğluna inanılmaz pratik imkanlar sunmaktadır. Nobel ödüllü fizikçi Richard Feynman'ın maddenin atomistik yapısının doğrudan manipülasyon olasılığının ortaya koyacağı pratik imkanları kastederek bir zamanlar altta çok yer var diyordu. Günümüzde malzeme bilimi alanlarında yaşanan gelişmeler, ünlü fizikçinin bu vizyonuna ışık tutmakta ve yeni boyutlar kazandırmaktadır. TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün disiplinler arası seminer serisi bu konulardaki üst düzey ve yenilikçi bilgileri ülkemizin bilim ve mühendislik camiasına aktarmaktadır. Bu akşam yine bu kapsamda bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Bu akşamki seminerimiz Massachusetts Teknoloji Enstitüsü MIT'den dünyaca ünlü bilim insanı ve mühendis Profesör Zhu Li'nin katılımıyla gerçekleştirilecektir. Profesör Zhu Li, emsali görünmemiş özellikler için esnek deformasyon mühendisliği konulu bir konuşma yapacaktır. Saat biraz geç olmasına rağmen katılımınız ve ilginiz için çok teşekkür ediyorum. Hepinize saygı ve sevgilerimi sunuyorum. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Zhu Li, dear participants, dear colleagues and friends, hello everyone and welcome. Welcome to the inspiring online interdisciplinary seminar series of TÜBİTAK Research Institute for Fundamental Sciences. We organize this seminar series for national and international audiences, relying on the unifying feature of science for humanity, and with the participation of distinguished scientists and great speakers of the world. It is now my distinct pleasure and honor to introduce you our tonight's very special speaker, a distinguished scientist and world-class expert in the field, Professor Zhu Li from Massachusetts Institute of Technology, MIT. He has kindly agreed to join us for this seminar and is going to give a great talk under the title, Elastic Strain Engineering for Unprecedented Properties. At the end of the talk, we will have Q&A session where questions can be asked by sending a message through the chat button of the Zoom platform or just by raising hand. Zhu Li is an American scientist, engineer, and currently Battelle Energy Alliance Professor of Nuclear Science and Engineering and Professor of Material Science and Engineering at MIT. His group performs computational and experimental research on mechanical properties of materials and energy storage and conversion. Zhu obtained a PhD degree in nuclear engineering from MIT in 2000 and bachelor's degree in physics from University of Science and Technology of China in 1994. He's a recipient of the 2005 Presidential Early Career Award for Scientists and Engineers, 2006 Material Research Society Outstanding Young Investigator Award, and 2007 TR 35 Award from Technology Review magazine. Thomson Reuters included Zhu in its highly cited researchers list in 2014 among 147 global scientists in the material science category. Professor Zhu Li was elected Fellow of the American Physical Society in 2014 and Fellow of the Material Research Society in 2017. together with Bilge Yıldız, who was one of our speakers last year, he co-founded the MIT Energy Initiative Center for Materials in Energy and Extreme Environments. With this, I want to invite Professor Julie to the stage to begin his talk. Jo, good afternoon. We are very honored to have you with us. Please begin your talk.
Thank you, Alikram. Me too. I'm very glad and it's real honor and pleasure to be with you on this Saturday. So thank you all for sharing the evening. Let me share my screen. Do you see it?
Yes.
Great.
It's perfect.
Okay. So we all know that high pressure physics can induce amazing physical properties. For example, this is a piece of metallic sodium, which under 200 gigapascal pressure turns transparent in a diamond anvil cell. And recently, we've also known that we can use high pressure, this kind of pressure, to achieve room temperature superconductivity. What I want to talk about today, elastic string engineering, conceptually is a superset of high pressure physics where you apply equal triaxial compression. But imagine if, let's say, if we apply tensile stress in the y direction and compression in the x direction, then that's a shear stress. And in standard materials, however, you wouldn't be able to go very far before you trigger dislocation plasticity. Or if you decide to pull in x direction, that's uniaxial tension. And in conventional materials, you don't get to use very high stresses because you will either fracture or have plastic strain. And you'll be very far away from so-called ideal strength limit. So this is what a perfect crystal lattice can sustain at zero temperature without any defect. This is so-called ideal strength limit. I just want to remind everyone that we know metals can easily deform 30, 50%. But here in this situation, this is almost all a plastic strain. The elastic strain is typically less than 0.1%. However, with nanomaterials, there is something called a size effect, which is smaller is stronger. So what you see here are bulk nanocrystalline nickel. Their room temperature flow strength as a function of inverse of their grain size. And in something very soft as pure copper, so this is copper without any alloying element, just by reducing the grain size to tens of nanometers, you can have yield strength on the order of a gigapascal. So this is fundamentally because when you reduce the characteristic grain size or sample size, the strength goes from a defect propagation controlled to defect nucleation controlled, because these boundaries destabilize defect sources like the Frank-Reed source and fundamentally change the defect population dynamics. And this has been seen in, for example, nanopillars, that as we reduce the diameter of nanopillars, the strength goes up. And in the limit, you can get these nanowire strengths or nanoporous material strengths. They're all very, very high. And so we define ultra strength as a component that sustains a component level stress, which is more than 10% of its ideal strength. And ideal strength typically is on the order of 10% of the Young's or shear modulus. And so this column is from density functional theory, what the ideal strength of the lattice should be. And 10% of this is basically about 1% elastic strain. So if you have a material which can, at the whole component level, sustain 1% elastic strain for a very long time, like for a few years, then we call that ultra strength. And in these materials like carbon nanotubes zinc oxide nanowires, nanoparticles, nanospheres, and graphene. This column is the experimentally measured tensile strengths. And we can see that you can get 30, 50, and sometimes even exceeding the theoretically computed ideal strengths a little bit. As an extreme example of this, consider two-dimensional graphene. And in 2007, we, from density functional theory calculation, predicted a strength of about 110 to 120 gigapascal in tension. And then a year later, there was an experiment that gave 130 gigapascal. So here is the calculation, 2007. What you see here is the phonon, basically the vibrational dispersion curve of stress-free graphene, and you don't have any phononic band gap. But as you pull the graphene biaxially to about 20% in different directions, you actually really change the phonon dispersion curve. And there is actually a wide phononic band gap when you go to above 100 gigapascal strength. So in the experiment by Columbia University, what they have done is they have used a AFM tip whose tip radius is from 16 to 27 nanometers, and they poke on this monolayer membrane, which is 1 or 1.5 micron. And what they found out are two things. Number one is to fit the load displacement curve, they need a nonlinear constitutive relation. And number two is that at the point where it breaks, the stress right beneath the indenture is on the order of 130 gigapascal. And that means that right before the graphene breaks, it's fundamentally a different material from the stress-free graphene, because many physical properties like thermal conductivity, thermal electricity, superconductivity, of course, depend on the electronic and phonon band structures, and they really change under stress. So this is a very famous map called the Frost-Ashby deformation mechanism map. And so horizontal axis is the temperature normalized by the melting point. And then the vertical axis is the deviatoric shear stress. So the non-hydrostatic stress normalized by the shear modulus. And this 10% is where the ideal strength roughly is. And in traditional materials at low temperature, this is the yield. At high temperature, you have Cobo creep or Nabarro-Herring creep. And in the middle, intermediate temperature and stress, you have the hybrid diffusive displacive plasticity like power law dislocation creep. So generally we see that conventional material, they would have this inelastic relaxation. They would have inelastic deformation very far away from ideal strength limit. However, with nanocrystals, thin films, metallic glass, nanowires, nanotubes, nanodots, we actually now have a lot of materials with strengths at this level. And fundamentally, it's because this was for conventional coarse-grained material with 100 micron grain size. All these deformation mechanism maps, they would shift when we reduce the grain size or the thin film thickness or the sample size. And that is the intrinsic reason that we modify the defect population dynamics that enables we to have very high strength. And already this effect was taken advantage of by the semiconductor industry in so-called strained silicon technology. So what you see here on the substrate is a silicon germanium alloy. And this is, on top of it, is an epitaxially deposited silicon, which is under a tensor strain of 1% in both directions. And the reason they do this is because this is shown to improve the velocity of electron by a factor of 2. So you get faster transistors, and this is actually one of the main reasons for the delay of the breakdown of the Moore's law. And the reason that we can do this 1% strain, if you try to put a tensor strain of 1% on a macroscopic silicon wafer, it's going to fracture way before this. The reason we can do it is because this is a nanomaterial, this is 50 nanometers. So this is less than 10 nanometers thick. However, what we are right now driving is way bigger than 1% tensor strain. So what we try to do is 5%, 10% elastic strain in so-called deep elastic strain engineering. And this is in collaboration with Professor Yang Lu at City University of Hong Kong, where we have a silicon 110 nanowire that is glued to a MEMS device. And we found that it can be strained to 13, 14, 15% tensile strain, and it's very reversible until toward the end, it fractures. But before that, it's really elastic and reversible deformation. So a natural question is, with 15% strain, 15 times bigger than what we are using industrially, what can the physical property be? And just this year, we have also shown this is doable on diamond. Now, diamond is like the Mount Everest of electronic materials because of very high carrier mobility, very high thermal conductivity, very high dielectric breakdown strength. So you can really use it for high power electronics, high frequency devices. And also, diamond is ideal platform for photonics, also for quantum computing with the nitrogen vacancy defect. So what we have here is a microbridge that is several microns long. And furthermore, we have 3 of them together. And we pull it up to 5%, up to 7, 8% together. And this is also not a nanowire. This is actually just use focus on beam to sculpture it. So this demonstrates the possibility that it may be scalable to wafer scale to have arrays of these microbridges, and each microbridge may contain thousands of transistors, because right now the transistors are below 10 nanometers in size, or quantum sensors in one of this bridge. So, this actually is nothing new, right? Elastic strain engineering, every physicist, would appreciate that if you change the lattice parameter or you change the bond angles, you're going to have different physical properties. So indeed, at the dawn of semiconductor physics, Bardeen and Shockley have already discussed so-called piezo conductivity, which is how would the electronic conductivity, like mobility of silicon or diamond, would change with strain. However, in those days, they only use this deformation potential theory, which is basically a linear response theory. So people have tools like K dot P or deformation potential theories. These are all linear response theories. What we have done in collaboration with Professor Alex Shapif and also Professor Subra Suresh is to use machine learning and see what this deep strain space can give us. So we have done high-powered calculations using many-body GW calculations, and we are basically learning the band structure, which is a function of the wave vector. So this is 3-dimensional. It's also a function of the 6-dimensional strain. Strain is a matrix is a symmetric matrix. So it has a 3 by 3 and 6 independent components. And also there is an integer index. So we try to learn from the high-powered electronic structure calculations and basically represent the band structure with neural network. And it's actually quite difficult to visualize, that kind of high-dimensional functions. So what you are seeing here is the band gap as a distribution of band gap as a function of the elastic string energy density, because this is a scalar in milli-electron volt per cubic angstrom. So this is how much energy you're willing to put into the crystal. And for, let's say, 5 MeV per cubic angstrom, there is actually infinite combinations of elastic strain, which will give you this kind of elastic strain energy density. It could be compressive, it could be shear, it could be tension. And the blue color is the distribution of the band gap. So it means that silicon can be anywhere from 1.2 electron volt band gap to a metal 0 band gap. And now you may ask, okay, where is that experiment 5 years ago on the MEMS? This was the experiment 5 years ago. Okay, in fact, if we are able to further increase it a little bit, we would have this red island. And this red island is a direct band gap, because we know silicon has indirect band gap. But if you are willing to strain it further than this a little bit, the prediction is we can have diamond cubic energy based in silicon. So without phase transformation or fracture, you can have silicon becoming a direct band gap material. And so maybe you can make miniaturized lasers, you can make better photovoltaics with it. And so without strain, silicon band gap is the well-known 1.1 electron volt. But if you're just willing to pay some strain energy density, you can make it into an infrared detector if you want. And in fact, this red dot is the sort of the most cost-efficient way to reduce silicon's band gap to the metallic state. And so this point is what we call the first metal of silicon. It is still an indirect metal. However, if we trace this sort of steepest descent in strain energy for the band gap, it is, when we look at the 6 strain components, it's actually not a straight path. And so actually nature throws a curveball in sort of baseball language in this 6-dimensional strain space. And so if you do linear response theory, you get this initial directions, but you will not be able to predict this kind of first metal of silicon accurately. So this is one use of machine learning in strain engineering, that you see these nonlinear behaviors. And we can use a machine learned model to also look at topologies of band structures. And this looks like, for mechanical behavior people, this looks like a Tresca yield surface. But what it is really is in strain space. So these are the 3 principal strain axes. In strain space, what strain give you 0.9 EV band gap? So the iso band gap surface. And so we see it is piecewise continuous, but then you have these ridges, and 3 ridge lines come to a cusp point. And this is because band gap is the difference of 2 quantities, the conduction band minimum, the valence band maximum, and each of the CBM, you can have a crossover. So we can use machine learning to classify the symmetries of these symmetry switchings in the iso band gap surface. And after our 2019 work, we have now extended this work to more powerful neural networks. And we're able to study that of diamond. So you can make diamond from wide bandgap semiconductor 5.5 EV band gap all the way to metal, still staying within the phonon stability range, and you can make diamond direct bandgap material as well. And now, for those who have worked with neural network, we have, for example, done quite a bit of fitting interatomic potential with neural network. There is an issue of kind of taking derivatives of this network that sometimes is a bit noisy. And so in this particular case, we are looking at the second derivative of the electronic band dispersion, which is the effective mass matrix. And we're able to show that this improved neural network can actually give this second derivative, which is the effective mass, which is related to the mobility of the carriers pretty accurately with experiment. And we're able to use such machine learned band structure and elastic string energy density to drive finite element calculations for geometry like these diamond nanoneedles, which are actually currently being used in this thin field effect transistors. So this is very useful for designing strain engineered devices using the ab initio as a constitutive relation. And for diamond, as a function of strain, you can either have an indirect semiconductor in some regime, and then you can go to a indirect semiconductor here. You can go to an indirect metal, or you can go to a direct metal or a direct semiconductor. So these kind of like a phase diagram in the system, we can predict the phonon stability boundaries. So not only the electronic band structure, but where the phonons may turn to have imaginary frequencies that actually define the lattice instability and the ideal strain surface. We're able to visualize it in the 6-dimensional strain space with machine learning. And this is a very powerful tool. So next, I want to talk about application of this approach a bit. And I just want to say that everybody appreciates chemical metallurgy. So we have the Bronze Age, we have the Iron Age, we have the Silicon Age, and but if you think about why we come up with magical chemistries like this, it's not because our ancestors knew quantum mechanics. It's not even that they know that much of physical metallurgy. It's purely because that people make structures by casting, meaning you have a liquid melt and you solidify it. And the liquid composition is a continuously tunable vector. And generally, if there is any property that you care, then generally there is no symmetry principle that say that that property is maximized. And so if, let's say, too much tin is bad, for, let's say, the hardness of a metal, then let's try to reduce the amount of tin in the liquid melt, right? So that's all there is. And in 1959, Richard Feynman gave a very visionary talk at the APS banquet. The title of the talk is "There's Plenty of Room at the Bottom." He's talking about what you can do with miniaturization, and in particular, what is beyond just basic geometric scaling. So he was talking about things may stick and you need like 100-liter hand to move the gadgets. So he's talking about this non-simple geometric scaling effects. And we believe that with the elastic string engineering, you can have plenty of room in terms of the elastic strain that you can play with. Because generally, you can take anything you care, electronic, magnetic, optical, phononic, superconducting, thermoelectric properties, or even chemical catalytic properties, anything that you care. And generally, there is no symmetry principle that say that that property's derivative at your pressure equal to 0 state is optimized. And so you can always, if sharing in some direction is not good, you can try to share in the other direction. And so before the invention of the atomic force microscope, we have quite a bit of high pressure physics already. And there is, physical metallurgy, but you don't go very far with that. However, after 1986, there was suddenly a huge explosion of bulk nanocrystals, nanowires, carbon nanotubes, graphene, things that you can really pull on. And that really creates an explosion of possibilities for strain engineering. So I would like to first talk about this molybdisulfide monolayer material, because people have already shown at room temperature they can sustain 11% tensile elastic strain indefinitely. And what we try to think back in 2012 is, imagine you have this monolayer and you make a triangle so that the cross-section reduces as the distance to the origin, so it goes as R. Now, if you pull in the center, the total force is a constant. But that means that the stress would be diverging as 1 over R. And that means the elastic strain would go as 1 over R. To the origin, it's going to be higher and higher tensile strain as you go toward the origin. And then you would have a band gap, which would also shift as 1 over R. And then you would have basically a quantum dot if your band alignment shift as 1 over R, which would be like a hydrogen atom. But it would be a 2-dimensional hydrogen atom, that's first. And also it could be much bigger. It could be a few microns. It can be much bigger than a real hydrogen atom. So we call that artificial atom. And there could be 3 situations. If you pull in the center here, your CBM could be going down as 1 over R, and your VBM could be going up as 1 over R. And so at different locations, you could absorb different color photons, and then the electron could be going to the origin, and then the hole would bubble up also to the origin, and you can separate the electron hole at the origin. So we call that type 1 solar energy funnel. But you could also have the electron on the CBM going to the origin, and then the hole bubble up to the edges. Or because of strong Coulombic attraction between them, you have this charge neutral exciton, and then the electron drags the hole towards the origin. So that's what we call type 3. And that will be quite different from the standard photovoltaic materials, because standard photovoltaic, you have this electron hole pair, they would undergo random walk by tens of nanometers until they hit an interface with a built-in field that can separate the electron from the hole. But in this case, because you have this band gap gradient, you can actually induce drift of this charge neutral exciton. And when we put in the numbers, we predicted that this exciton can drift by microns. And so you can have micron-sized 2D material as a solar energy absorber, but you only need to separate the charge at the origin of this artificial atom. And here are the calculation results. So this is the electronic dispersion as a function of strain. This is the optical absorption spectrum from 0 to 9% strain. It shifts from something like 2 electron volt to close to that of silicon, 1.1 electron volt. And then from the band alignment, it's either type 2 or type 3 solar energy funnel. We believe it is type 3. In fact, this is artificial atom. You renormalize the divergence because it's not infinitely sharp. There is like a nucleus to this artificial atom. And you can use this to absorb different colors of the solar spectrum. And we believe it is type 3 because when we use the Bethe-Salpeter equation to calculate the exciton wave function, so this is you have an electron position and a hole position. So this is a 6-dimensional wave function. And this wave function is about 4 nanometers in diameter. So it's not a small polaron, and that's why we think it's going to have a good mobility. So that's why it's going to move quite far distance. But it's not easy to separate them because it's 2-dimension material. There is strong Coulombic attraction between them. And so we believe it is going to be type 3. And then there were some experiments. So a year later, people put molybdenum onto this polymer PMMA and they bend it. And on the tensile side, you're going to basically apply tension to that monolayer molybdenum. And even though the amount of strain is not big, it's only 0.5%, we see there is a visible shift in the photon absorption as well as the photoluminescence spectrum. And the measurement is 70 milli-electron volt per 1% of strain. And the calculation was like 100 MeV per 1% of strain. But in this experiment, this is only uniform tensile strain. There is no strain gradient as we predicted. But then there was this experiment from the Netherlands where they made this what we call a rip location. So you have this basically a wrinkle of molybdenum sulfide, and at the valley here, the band gap is higher, and at the crest, the band gap is lower. And so they cited our paper and they demonstrated that indeed the exciton can drift hundreds of nanometers. In other words, they absorb the blue light here that excite this electron hole pair, which then move to the peak of this rip location and recombine there and re-emit as a red-shifted photon. And that verifies this inhomogeneous strain engineering approach. Here, the strain is the bending curvature. So that was, photon in, and you try to get electron carriers out. There is also a opposite demonstration, which is what if we send electrons in and collect the photons? So Ji was my postdoc. He went back to Peking University and collaborated with Professor Da-Peng Yu. So what they did was in the scanning electron microscope, they have a photon detector, and they just use the electron beam to scan here, here, here, here. And they move from the outside to the inside. And as they excite this zinc oxide microwire, the diameter is about 4 microns. The light detector just analyzed the color of the light. What they found was that in this region, where there is no bending moment, doesn't matter where you excite the zinc oxide, the color of the light is monochromatic. But in this middle region too, when they scan on the tensile side, the color is this monochromatic red light. But as they scan towards the compressive side, there is a blue shift of the light. And depending on where the electron beam scans, the color of the light shifts. And so we fitted the profile of this microwire. We did some DFT calculations, and we wrote down this transport equation where this n is not electron density. This is the charge neutral electron hole pair density, the exciton density. So D is the random walk, the diffusivity. This is the drift term. So D over KBT is the mobility. This is the band gap gradient. But because the band gap depends on strain, this is also the strain gradient. And then this G is the delta function. That's the electron beam that we aim at the material that excite the electron hole pair. And then this N over tau is the photon that comes out with a single relaxation time approximation. So when we put in reasonable numbers for zinc oxide, we're able to fit the spectrum. And it's really very simple picture, which is, it's like your kitchen sink where, it's the lowest. If you aim the water of the faucet at the center of the kitchen sink, because the band gap is already the lowest, the electron hole pair just pull around that lowest point a little bit, and they just drain out of the system as this red light on the compressive side. But as you aim the faucet on the side of the drain, there the electron hole pair have a higher band gap, so they would actually flow towards the center of the kitchen sink. And at steady state, this is kind of the distribution of the electronic excitation in this nanowire, and so you would have this broadening of the light color. And in fact, you can also apply a longitudinal strain as well, and you can basically interpret the color spectrum. Now, those two examples demonstrate you can use strain to regulate the flow of photons or electrons. So that's enough for IT because you really don't need a lot of material. In fact, in your computer chip, in your laptop, you probably only have this much strained silicon, and that's enough. But because I work on energy, and anything in energy, you have to at least do kilograms or tons. So the question is, can you scale up elastic string engineering to kilogram scale? I mean, regardless, is even like catalysts or even superconductor cables or batteries or fuel cells. Anything you need for energy, you got to be able to do tons or even kilotons, right? So I do have an example of that in one metallurgy example. What we had was niobium in nickel titanium matrix. So we know that, so this was actually made by eutectic certification, where you have this niobium rods, which are microns in diameter. But then my collaborator, Professor Yishan Cui, did very careful wire drawing tests, and he was able to do the wire drawing so those micron niobium rods becomes tens of nanometers in diameter, and it's also embedded in this nickel titanium shape memory matrix. And if you have an individual niobium nanowire, it's very easy, in the transmission electron microscope or in the MEMS device to stretch it to 8%, 7% easily. But in this macro wire, this is millimeter in diameter cable, you would have 10 million of these niobium nanowires. And the question is, can these niobium nanowires strain to high to deep elastic strain? So this was, after the wire drawing, you have 10 million of these niobium nanowires embedded in a shape memory matrix. So this was the first tensile strain. And for metal wire, for metal cable, this is not surprising, right? You can strain a metal by 6%. But if this were plastic deformation, as you unload, you would unload to here, you would have 6% plastic strain. But in this material, when you unload, it goes completely back to 0. And so there is some hysteresis because of the phase transformation of the nitinol matrix. But overall, this stress is very high. It's above 1.5 gigapascal. And the effective modulus is close to that of the human bone, because initially Professor Cui was trying to make this orthopedic material where, for the orthopedic implant to prevent the osteoporosis of bones in this hip joint replacement. But later he found that actually this is actually useful for superconductivity. So what is really interesting about this material is that it's kind of in between a polymer and the metal. And so just to demonstrate that this is real. So we have done at the APS at Argonne in situ synchrotron diffraction. So this is the niobium 220 peak, and I've never seen this before in my career, that you see such a huge shift in the XRD peak. So this shows that the niobium is undergoing a true elastic deformation. And what is very important is that you must have a shape memory alloy matrix that's undergoing this B2 to B19 prime phase transformation. Because if we just tune the alloy composition a little bit, just change the composition a little bit to have even just a little bit of dislocation slip, boom, we see the elastic strain limit of the niobium drops from 6% by a factor of 4 to 1.5%. So the key idea here is that to preserve the huge true elasticity of the body center cubic niobium, it must be matched by this phase transformation pseudo elasticity. The reason is at the atomic scale, if you have a dislocation slip, you have the Burgers vector divided by the lattice spacing, which is more than 100%. So when a dislocation hit this interface, at the atomic scale, it's a very sharp knife, and that's very easily destroy the true plasticity of the niobium. Remember, the whole reason we have high elasticity in this nanowire is because we suppress dislocation nucleation. But if you have dislocation which is piled up on this interface, boom, you would reduce that strength limit. But if you have this B2 to B19 prime phase transformation, at the atomic level, it's only 7%. So that's a much blunter inelastic deformation, and that preserved the good elasticity of the niobium nanowires. So we call this the inelastic strain matching design idea. And so, what it is useful for is, well, niobium alloys is actually the most commonly used superconductor in maglev trains, in magnetic resonance machines, in particle accelerators, in tokamaks. And when we adjust the wire drawing procedure, we can actually lock in this residual elastic strain on the niobium. And from our initial calculation, we predicted that the superconducting temperature would actually shift. Okay, so this is the experiment. The superconducting temperature shift from about 4.5 Kelvin to about 5.2 Kelvin by about 0.7 Kelvin. It doesn't sound like a lot, but remember that you're going to use liquid helium cooling. And so you actually increase the engineering margin for cooling these devices. And the other the point is that the upper critical magnetic field and the lower critical magnetic field also improve quite a bit with the retained elastic strain. So this is a demonstration of bulk scale, kilogram and kilometer long composite superconductor cables where you can do strain engineering. And more recently, there is another demonstration on this nickel titanium iron metallic glasses, where we are able to demonstrate kilograms of metallic glasses strained to about 6% elastic strain. And actually, metallic glass are used for the soft magnet cores of transformers. So this again, I think studying the magnetic properties of these materials is of interest. So in the remaining 5 minutes, I'd like to just say that general strain engineering also include inelastic strain, obviously. And in this 2D material, for example, we have looked at inelastic strain, such as this so-called H to T transformation. So most of the monolayers have this mirror symmetry. So you have the sulfur having a mirror symmetry, but no inversion symmetry. It's like a hexagonal closed pack structure. And that's a semiconductor. But the T structure is like the FCC structure where you have the inversion symmetry about the middle plane transition metal atom, but you don't have the mirror symmetry. Now, the T structure turns out to be unstable, and it will undergo this pulse reconstruction to this 1/2 reconstructed called 1T prime structure. That's also a semiconductor. And because you have one of these three reconstruction variants, so there are actually three shear strain variants, and that would give rise to this martensitic transformation and the ferroelasticity. So we have predicted, for example, this T prime to another T prime variant twin boundary is very glissal. So when you strain it, it's going to have very mobile twin boundaries. And so when you look at molybdenum and tungsten, sulfide, selenide, and telluride, then we found that all their T structures are unstable. They're going to reconstruct into this 1T prime structure, but only the tungsten ditelluride have a lower energy than the H structure. As also the moly ditelluride is kind of similar. The other ones are thermodynamically only metastable compared to the H structure. Now you may ask, what might be the T prime structure be useful for? Well, we have done this band structure calculation, and it's very interesting that, in most cases, the chalcogenide, it takes electrons, right? It takes electrons from the transition metal. The transition metal donate electron, the transition metal D is higher in energy than the chalcogen P orbital. However, after this T to T prime reconstruction, after this pulse distortion, you actually tie a knot in the electronic structure where in a certain region of the wave vector space, the chalcogen P actually have a higher energy than the transition metal D. And in fact, the chalcogen would actually lose charge to the transition metal D. So that's an anomaly. And it shows up in this 1T prime tungsten ditelluride. But unfortunately, so you do open up this spin orbit coupling gap here. But unfortunately, it's also an accidental metal. So you actually need to have a little bit of strain, about 2%, to open up this accidental metallicity, but still preserving this fundamental band inversion. So in 2014, we predicted this T prime structure will be a topological insulator if you just apply a few percent strain. And that was indeed verified 3 years later by RPs in monolayer. We predicted it has to be a monolayer. If it's a bilayer, it wouldn't work. It would be a normal insulator. And then later at MIT, Professor Pablo have shown that the edge conductance is this perfect E square over H quantum conductance. And furthermore, this has a very interesting magnetic field dependence because there is a spin orbit locking, and this persists up to 100 Kelvin. And later, they've also found that this monolayer tungsten ditelluride is also a superconductor. So this opens a possibility for this topological quantum computing as well. So with that, I'd like to wrap up and say that, we've heard a lot about, chemical alloying, but I think strain engineering is like the ultimate mechanical metallurgy. Is going to compete with chemical metallurgy. But the reason, we haven't heard too much about it yet is because you really need to have 4 pillars simultaneously. And these pillars just historically was not available. So the first pillar is you've got to be able to make materials and structures which can take 5% shear, 5% tension. And the carbon nanotubes were synthesized in 91, bulk nanocrystals in the mid-90s, thin films, graphene 2004. So previously we don't have, but now we almost have like too many of these structures which can sustain big deviatoric shear or tensile loading. Number 2 is you got to be able to apply force or stress at a nanoscale and at the same location measure the change in your optical, electronic, or chemical properties. And AFM was invented in '86, and you have nano-indentation developed later, and now you have a lot of lab on a chip or nano electromechanical systems. And so now you really can do this, but 3 decades ago, you were not able to do that. And also, let's say you want to have, let's say a piece of germanium at 70 Celsius under 6% strain for 3 years, so you can use it in your cell phone, but after 5 months, you found that strain is gone. You want to know what's the reason for the inelastic relaxation. Was that dislocation, nucleation from the surface? Was that diffusional creep? Was that fracture? Was that phase transformation? So you need this deformation mechanism studies using extended timescale atomistic simulations. So in my group, we develop those kind of methodologies to study the rare events of defects, or you use in situ TEM or synchrotron to understand the deformation mechanisms. And that was really developed in the last 20 years. And however, I just want to say that also the philosophy is quite different. We are trying to understand these deformation mechanisms not for forming operations, like in traditional mechanical forming, but we are trying to understand them in order to defeat them, in order to understand the time, temperature, strain or stress, and the property envelope within which you can engineer these materials for devices. Okay, so the goal is to not have them and to defeat them at room temperature for a few years. And lastly, we are, after all, no longer in the Stone Age. We have very high-powered DFT and extended excited state methods. We can do machine learning, conceive relations, so we can predict what is the ideal strain surface and answer questions like, if you give me strain in this direction for 70% of the ideal strain, how much benefit would I have in terms of physical properties? And already this approach has commercial success in lasers in the 90s, and then IBM and Intel took it to big time. In fact, at MIT, we've had people who made a great contribution to strain silicon technology. And now this is really multi-billion-dollar industry. So I'm very optimistic that with as time goes on, strain engineering is going to contribute a lot to our civilization. And this is just showing that in my lab, in the last few years, we're developing these MEMS devices, which can actuate a 2-terminal device. And we're now designing 3-terminal devices. And we're also doing a lot of the TCAD simulations as well as optimization with the goal towards a 3-terminal device demonstration. So with that, I'd like to thank you for your attention and be very happy to answer questions.
Thank you very much for this very exciting and impressive, comprehensive talk. Indeed, you have formulated many interesting questions and answered them, Nevertheless, maybe we can ask still a couple of questions. Please ask questions or send message, or just by raising hand, use microphone. Questions, please. So let me please ask one question. As a physicist, you are also a physicist by origin. So as far as I understand, you tackle all components of strain tensors using machine learning and classifying symmetry structure. So I wonder, are there any critical symmetric structures that give us very striking results? one can by using symmetry make, what was this one? Make equal to to zero some components or diagonalize and so on, so on.
So far, according to our experience, we haven't found. Yeah, so far, we haven't found very special symmetries. I mean, certainly for shear strain, let's say positive shear strain with minus shear strain, there might be some kind of inversion symmetry in that, but definitely in the normal strains, so far, there is really no special symmetry for properties that we have found. So in other words, if you try to extremize most properties, you would actually have some looking like pretty random strains to optimize real figure of merit. So that's our belief that actually there is not a very special symmetries in the strain space which give you your best properties, because very often your property, let's say thermoelectric figure of merit, is a compromise between thermal conductivity, electronic conductivity, Seebeck coefficient. So when you have those real figure of merit, according to our experience so far, you don't have special symmetries.
Mm-hmm. Thank you. There are a couple of questions on chat. Can you read them?
Yes.
Or shall I read for you?
No, I can read it. The first question is, what is the effect of self-similarity or fractal on the strength? That's a interesting question, because I think what you mean is, as you reduce the size scale, there is a power law scaling, like the Hall patch relation on the strength. So in that sense, the exponent is very often minus 0.5. So if you reduce the dimension by a factor of 100, let's say you go from 100 micron to 1 micron, your strength goes up by a factor of 10. And that's really the reason that we have this big explosion of that. That is the reason we have this big range, a much bigger volume, right? Because the strain is 6-dimensional. So if your strain limit increased by a factor of 10, your parameter volume goes up by by a factor of 1,000,000. So that is indeed the fractal dimension of 0.5. Another question is, in which media carrier transport exhibit anomalous diffusion? What is its importance? I think by anomalous diffusion, you mean it's not just traditional random walk, there are some exponent. I think so far we have not paid attention to that. Now that's a great question, the Levy flight. So far in our model, we assume it's like a normal diffusion, and that seems to fit the device characteristic reasonably well. I know about this non-random walk transport, but I think most people in TCAT simulation in electronics, I think they just have this standard normal diffusion term. So not quite sure about abnormal diffusion. Thank you.
More question, please. So people, thank you. So
thank you.
Yeah. So if no more question, it seems that no more question, Zhu. If you want, you can make a final remarks, and after that we can close the session. Is it okay?
Well, yes, it's really an honor and pleasure to spend the weekend evening talking about physics and mechanics. So thank you very much for your attendance.
Thank you. thank you very much. It was great pleasure to listen to you. And I hope that the same will happen in person in future.
I hope so.
So bye for now.
Good night. Bye-bye.
Bye.